And we're being recorded. So we are on exam one review session for ME470. There, Nathan. Nathan's coming. All right. And March 4th. Man, time is flying. And spring break's after next week, right? Sure. Okay. Silence implies consent.
Oh yeah, it is.
So chapter 13, chapter 14, and chapter 11. Here's some problems Dr. Ghosh used to, these are the ones that he used to suggest would be representative of stuff that you would want to be able to do. Although some of them are way too long to do for an exam. So, but if you wanted to look at some extra problems, and aside from the ones that I posted, can you reshare your screen? I can't see it. This happened the other day, didn't it? Interesting. Let's reshare the screen. Do, 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 do. I had all kinds of technical difficulties last night at my gig. It always happens to me for some reason. It's not me, it's you. Can you see it now? How was the gig? It was a not my best performance, and my mixer was going crazy because it's like this dated technology of mixer by its line 6 stage-scape thing. Still can't see it for some reason. How about Dylan? Dylan and Des Moines. Can you see this? Can you see the screen?
I,
I
I,
can see
I,
the
I,
screen.
I can see it as well.
Nathan, it must be you. Okay. Yeah. Take off and come on back. Yeah. So my yeah, we don't want to hear about my gig. I won't waste any more time. But anyway, it was an adventure. All right. So yeah, so these are, let's see, these are the problems. Yeah, okay, so I have the problems listed out from the suggested ones, right? And boy, the clarity isn't all that great for definitely not very good high resolution. Definitely not doing this problem. Okay, so we're not doing this problem. It just happened to be on the list, man. I was just using the list. This is a challenging one right here for planetary gear. You know, planetary gears are on the table. Another planetary gear, also a challenging planetary gear. I think the big challenge is trying to figure out what this diagram means. That's the hard part. I'm just going to go cycle through these, kind of see what this is the menu, and then you guys can make requests if anything jumps out at you. So maybe consider that as we're walking through. And once again, I just tried to pick out some stuff that pick out some problems. I was like, hey, this would be the kind of thing that I want you to be able to do, but not necessarily representative of this is the problem, right? Um, if you've had me before, you should recognize that I don't just give away, okay, here's exactly what you need to do for the exam. If you want to prepare and see, can you do something? Right. So I was talking while I was going through some of these right here. There's usually chapter 4. So there's a chapter 13 thing, and yeah, this is okay. This is a sort of a basic problem, right? We did several problems, kind of like that. So here's some stress problems, and this is you could do this either way with AGMA or non-AGMA. Same thing true with this. There's another stress problem. Look at Osama's got his hand up. You can
Sir, where do we find these slides?
you find them right here, my friend.
Okay. So they're not in Blackboard.
Okay, yeah. Well, they're problems that are going to be. Let's see. I'll show you where they are. I'm sorry. I was just joking around, man. Right in the beginning, when I started here, let me see. I'll try one more time there, Nathan. Let's see what happens here. I apologize, Nathan. I just don't know what's. what's causing that. If you go to, bring it over here, boom, and if you go to exam prep, these are the problems right here. So that's what I'm doing right there. So you don't need the slides for them because you have the book, right? That's these are the, what is that thing right here? You have 151 registry issues on your PC. That's great. Thanks, man. And then we also have answers, right? So there's the ones that say, yeah, okay, so these are suggested problem answers. And here's a suggested problem. So you get those from the book, and here's the answers from right there, right? So that's that's what that's what these are. And I'm just kind of flipping through them here to start with, so we can kind of see what our menu for eating today is. I guess we're not eating. Here's a contact stress problem. Yeah, I think this is an AGMA problem. Could we do one of the planetary gear if we want to start? Okay, absolutely. Okay. More spur gear stuff right there. An AGMA method. So we got some bearing ones that are going on right here. And this one I just threw the answer right in there. Solution manual. Oh, okay. I'm doing it right there too. Anyway, so we can look through some more of this. Then we also, I was actually looking for, okay, here's exam practice problems, right? So can we do one that consists of FBDs, maybe like four-star chef? Yes, absolutely. Okay. So let me go back up to, sorry for the delay here. So let's try one of these challenging planetary gears from the textbook. There you go. One of these two right there. This one and this one. They don't have a whole lot of them. So I'll try this one. All right. So the gear numbers for the gear train that we see right here are 20 teeth. For this guy's got 20 teeth, and this one has 16 teeth. As we're going through here, we want to check out some of the diagram here. You can see there's a dashed line like right there. That means that this is spinning freely on this shaft, right? And then it goes to gear 4, which has 30 teeth. But you can see because of this little fillet right here, they're implying that this shaft and gear spin together. And then you can see the dashed line through here means that this gear is attached to, so 4 and 6 are fixed onto the shaft and they'll rotate together. And 6 has 36 teeth, and then we come down to 7 right here, and you can see from this dashed line that this shaft spins through 7, and you can see from this little black gray area right here that 7 is actually fixed, right? And 7 has 46 teeth. So that's sort of the situation as they set up, and we could probably look up in the Levi or the Levy, and this is a planetary gear set, but it's really kind of hard to picture, I think. So let me turn my camera on. All right, camera. Where at camera? Camera. There you go, camera. I gotta see the problem too. Maybe I have it in here. I should have brought the book home. It's gonna show the back wall first. I was gonna try the front facing camera. Now it's gonna try to show you the back facing camera. There's the back wall. I definitely need to change the wallpaper in this room. So let's see here. Bearing problem. There's a bearing problem there. Do I not have this written down? Okay, well, we'll just have to move this thing over. Okay. Well, I gotta see. Probably I'll bring it over here. All right, so I don't necessarily have to draw the whole thing out, but I like drawing things out to help me think my way through the problem. All right, so let's see, this is got 30 teeth. I'll call them T's. And this is 6. All right, so this is 4, and this is 6, and this is 36. And it's going, here's the carrier for the thing. And then they have this gear right here. And he rotates along those lines. And coming through here, and then here's, I kind of made the thing too big, so there you go. So this one is fixed, and this is what 46 teeth, and this is sort of the shaft that we want. And lastly, we have a gear that looks like this right here, and he's right here. And so this is number 3, and this is number 2, and 3 has 16 teeth, and 2 has 20 teeth. And we say that this rotates, is going to rotate 10 revolutions. And how many turns will the shaft of B make, right? So this is A, and this is B. And we'll just go ahead and say he's rotating counterclockwise. So our first thing to probably do, and we say that this is going to the number of turns. Let's just call it RPMs. We might as well call them RPMs. So let's say that this goes 10 RPMs, right? It doesn't really matter. I don't want my February report. Go away. Heck if he really, really wants my attention. It's like it's so I'll say that this NA is 10 RPM. So I'll start out with my E and march through, right? So there's my first gear. And so we say that's going to be, this drives this one right there. So N3 is driven. And then 3 drives 4. And then 6 drives 7. Even though 7's not rotating, right? That's just the way that we're referring to the thing. Noteworthy that 3 would cancel each other out. So you take 20 teeth times the 36 and divide by the 30 and divide by the 46. 20, 36, 30, 46. And we should have 0.5217 is our gear train ratio. And now we want to go to our book in chapter 13 under planetary gears, or and actually I'm not sure there is a planetary gear section. I think it's just in gear trains. And there you go. And we have our main equation here at the bottom. This guy right here, I'll write him down. E equals NL minus NA divided by NF minus NA. And now we got to see how that applies to our situation. Well, the last gear in this train is going to be the 7, even though it's not rotating. So it's going to be 0, right? And the arm is actually this output. You can see that's the arm onto the thing. And so this is the input right here, the first. So you got first and last. So we go 0.5. Oh, we have to decide. Oh, by the way, we need to assign a sign for this, right? So we have to decide, is the input and the output turning in the same direction? Because the sign of this will affect our result. So what I've been told is you hold on to the arm and then you see which way the last gear would rotate. And that determines the sign of this, right? So that's it. That's like a rule of thumb approach to this that I've heard multiple sources. I think it might be said in this book, but it's just a good way to remember. So hold the arm in place and see which way the last gear would rotate. Even though this is fixed, we're only doing that for the sign of here. So if this was fixed, all right, let's just march through this and do the little thing. You have to kind of picture what this thing would look like. I could try to sketch it if that would be helpful, but they're going to be superimposed on top of each other. But if that was gear 7, sorry, I never labeled it 7, right here, you would see that we'd have, I'll make this one much bigger. That would be gear 6 right up here. And then of course, gear 4 would be right here, right? And they rotate together. Gear 3 would be right here. And then gear 2 would be right there, right? So hopefully you can picture this. So I wrote, this one goes this way. This is 2, and this is 3. This is 4. This is 6. Where did 5 go? Oh, they numbered the arm for some reason. I don't know why. Don't ask me why. All right, so we could see that 3 would go clockwise. I'm assuming 2 is going counterclockwise. And I'm looking from this direction, by the way. Creepy eye. Right, so this is going that direction. So this has to go that direction. And therefore, you know, you could, I'm going to draw the arrow. This is the arrow for 6. And then, did I do that correct? I'm starting to think I did it correct. It says, oh, no, okay, yeah, we're okay. So here we go. So this actually should be, this goes in the opposite direction of this, right? So I think I did that correct. This is this is the way to assign the sign for this thing. You could also see, by the way, because we don't have another, and so we're saying that's going to be negative because this goes the opposite in this direction right there. So we've decided that must be a negative value. So when we go down here to plug it in for E, we'll make it negative. Another way that you could do it, because this does not have a gear with internal teeth. These are all external teeth. It would be true. There are 3 stages of gears. Every one of them is negative. So it makes sense. You have negative times negative times negative, that you get a negative result. So that is also true. What messes you up in that respect is if you have internal gears, right? Like a ring gear. That does not behave the same way. All right. I can't see the at the same. I have 2 monitors, but I'm using both of them at the same.
Sir,
So let's see. Could you do? Okay, can we do one? Or are you putting your hand up? I can't tell. Okay.
like for an did they tell us the shaft B doesn't rotate, or we assume that?
We tell that by no, shaft B does rotate. Okay, shaft B does rotate, but for the purposes of trying to apply the equations that we have for this, what we do a hypothetical. Okay, let's pretend that 7 rotates, even though it indicates that 7 doesn't rotate, in order to establish what the gear train ratio is going to be.
So the gear
train ratio, and we determine whether it's positive or negative, as if it could rotate. Okay, and now we go ahead and we apply what actually is taking place with the gear train equation.
Okay.
Right?
Thank you, sir.
No problem. So now we could go. So now we have that negative. We can go 0 minus. This is the thing we want, right? The arm. And the first we're going to say goes 10 RPM. And we're going to go to the arm again. And now we have a little bit of algebra to do. And I'm not really great at algebra. So I usually don't trust myself to skip steps. So I will methodically go through this and look like I don't know what I'm doing, which is probably true. All right, so here we getting says, are you putting your hand? Please go ahead and put your thing in the text, or I mean, yeah, I don't know. Go, you could do that. All right, doesn't matter. I'm just can't quite juggle these things sometimes. Just two monitors, and I need to look at one of them. So
I just had a quick question.
Okay, cool.
Why do we can we assume that the shaft speed of A to be any number, but we just chose 10 for this case?
Well, I just didn't like the way that the problem asks for if you turn it 10 times, how many times, A 10 times. I'm like, I'd rather think of it in terms of RPM. So I just gave it an RPM instead, right? Because
Gotcha.
I've seen students that got confused because well, we only did a problem where we turned it 10 times, but now you're asking for a speed. And I'm like, all right, it's a speed. I can't win. That's what I'm just saying. I'll confuse everyone, no matter what. So what is this comes out to like 5.217 plus 0.5217 equals negative NA. I needed NA right there, right? So I bring the thing over to the other side. So we got minus 5.217 equals, and now we're going to have what? Minus 1.5217 NA. Did I do that right? You guys can catch me anytime you want, please, to tell me I screwed the thing up. But now, okay, hey, that's good news, because we know the answer. 10 times that and flop that guy over and add 1 to it. Boom. And then divide. And do we get a positive 3.429? Call it RPM. And the slide that we had, bring him back over to the other screen here. Yep, we got the right answer. Woohoo! Off by a decimal place. But anyway, so that was sort of the general process. We could do another one real quick because they're not long problems, just to try to organize how you approach this. Once again, this doesn't have I should go back. Okay, does anybody have a question about the one we just did?
So with the original thought process of which ones are rotating and which ones aren't, how does that help us solve the problem in this case? Like for 3, you said the dashed lines mean that it rotates freely, independently from what exactly?
Okay, it can spin around this shaft, right? The shaft is just holding it there. It's just holding its position, but it's not stopping it from spinning. It can spin freely. Whereas 4 is attached to the shaft.
Gotcha. And then the dashed line through the center of 5 means that shafts that go through 4 and 6 are connected as well.
Yes.
Okay.
And that shaft can spin independently of 5.
Gotcha. That makes sense. Thank you.
Same thing's true for 7 right there. Initially it is difficult. Once you recognize and you see like what they mean, it becomes kind of obvious. But when you first look at this diagram, it can be pretty confusing. I remember being confused by it, thinking like, does this thing even work? And so here's like another one where there's a little bit confusion going on here. Almost need to make this thing much bigger. No, it's kind of stuck. That's the size it's going to be. Okay. There you go. To be able to kind of pick what's going on, because you have this arm and it's rotating. Yeah, this one always bothers me. Because in the reverted planetary terrain illustrated, find the speed and direction of rotation of the arm if gear 2 is unable to rotate and gear 6 is driven. And you go, okay, how is it driven? Well, there must be another gear over to the side. That's always confused me. This is a weird diagram right here, right? So this gear 6 is driven somehow that we can't tell. I don't know how it's being driven, because anything that you would be driving with is going to get hit by this thing that's rotating. So I don't know. I've always thought this was a weird problem. Like how would they be able to drive gear 6? It's just hard to picture. But gear 6 is being driven in the clockwise direction as viewed from the bottom of the figure. So I'll try my best. It's a weird one. It's a weird problem. So what was this previous problem? I should label these things. This was 1330, so I'll label that 1330. I'll put you up here. So what is this? 1327. I don't like this problem at all. Try to draw the thing out. This helps me think. I'll draw that as a thin line right there. So there's the arm. Start out with the arm here. And we have gear 2 is moving with this shaft, right? So they show like a little thing right there to indicate that gear 2 is attached to the shaft. And here's gear 6. Well, I'm going to make it, I didn't make it big enough here. It'll have to do. And then you have this gear and this gear, but they are attached to this shaft right here. And you almost have to erase some of these lines here. All right, so this is 6, 2. Here's the shaft, and now I've often thought that this should. I feel like it should be, but I think this is connected. They didn't put the little symbol signs on there to make it look connected, but this is definitely connected. And I'm regretting picking this problem. This guy is rotating through here. He's number 5, and here's number 4. And this guy has 16 teeth. He's got 30 teeth. He's got 20 teeth. And they didn't tell us how many 6 have. The plan is to find the direction. Okay. N of 6 is 12 RPM. But I think we can figure it out. Okay, so they didn't tell us the number of teeth of 6, but we can figure it out from teeth math, right? So the difference between here and here, if this has 20 teeth and this has 30 teeth, then there would be 10 teeth, or you could think of it, right? By the way, the teeth math, recall that, like, if we pretended that the pitch was equal to 1, then the diameter would be equal to the number of teeth. Are we okay with that? Would you like me to repeat that? Like, you're going to pretend P is equal to 1, therefore dn is equal to d, right? So we can, if we're doing that, therefore we can pretend that this 20 teeth means that this thing is 20 inches in diameter. So that means there's 10 inches right here. And that means that this is 30 inches in diameter, so that's 15, right? So the center to center distance between these two shafts must be, well, you could do it this way. You go 20 plus 30 divided by 2 right there. So anybody want to help me out with that math? It should be 25, right? That's 10 and that's 15. Yes, yay. So this is 16 teeth right here. Therefore, that's going to be 8. So therefore, 25 minus 8 is going to be 17. Is that right? Therefore,
Yep.
the number of teeth is going to be 34. Did I lose anybody on that? I don't know how to write it out, but all right.
So here we assume like n equals d.
Yes, we just assume just to make life easy. I'm only I'm just suggesting that's a good way to think of it. We could write it out a long way, and we could see that.
I think that's better. When you assume it like this, it's much easier to solve.
Yeah, it's much easier to just to consider it, think of it in those terms.
Yeah.
And by the way, let's see. I want to, before I forget right here, this is clockwise. Okay. So let's see the gear train ratio and coming through here. So because they described 6 as being the input, we'll say that's where it starts. So we'll say that 6 is going to drive 5, right? And then 4 is going to drive 2. So we can have 34 times 30 divided by 16 and 20. And we're gonna play that same game that we did before. A little bit, once again, the diagram to maybe look at this thing from from this direction right here. It's a little weird, but we could take a look at, we go 6, and here's 5, here's 4, and then here's 2. All right, so here's 6, 5, 4, 2, and they're saying this is going clockwise. So that means this is going counterclockwise, which means this 2 is going counterclockwise. Whoops, I did that wrong. It's all those errors are probably true, but let me step back. It's 6 that's actually moving, right? So 6 is going that way, and therefore 5 is going that way, and therefore 4 is going this way, and therefore 2 is going that way. So input equals output, therefore this one's going to be positive value. 34 times 30 divided by 16 divided by 20 is 3.188. And then we use our main equation right here. Once again, from in short attention span, Dr. Deal has to look at this thing again. And let's see what's being held in place. 2 is unable to move, right? So find the spin direction of the arm. It must be I'm a little frustrated right now. Just one second. It must be that this shaft passes right through there. and it passes through right through there. Take a look at the image again. Your image. And I'm sorry for, I'm actually sorry for picking this problem. It's Shigley's fault. It's not mine. But you see that like 2 is definitely attached to that shaft, right? We're all in agreement. And if 2 can't move, therefore, you don't see an attachment like kind of like, like that thing right there. That's sort of like implying that the shaft is attached to 2, and there isn't any right there. So this arm must be able to, and you also see it's not there as well. So they really should be drawing, I think, dashed lines through right there. Other instances that you can see that has that thing right there and right there. Those are all indications, like this shaft right there, that's attached right here, but this one's not. So that's, in my opinion, indication that it can rotate. I hope. Let's see. I don't know why I had to pull this back over. So anyway, 2, I'm going to consider 2 the last gear, because I started calculating. I started with 6 and ended up in 2 up here. So that's the way that I'm going to go with it. And so 2 can't rotate, 6 can. We're going to call that the first, and it's the arm that we're trying to find. So we'll say 3.188 equals the 0 minus the arm again, and this was the 12 RPM and the arm. And what we're left with is, we got to do the same thing again right there, right? We're going to go 12 times 3.182 minus 3.182 NA equals negative NA. So NA, which is the arm, so we're going to have 12 and then 3.182 1 there, and it's going to end up with a negative value. Yeah, negative. All right, we're going to add it onto there, so divide, and I get 17.53, and I'm not feeling a high degree of confidence that I didn't screw something up along the way. Oh, but I got it right. And so it's negative, by the way, so it's going to be counterclockwise. Oh, no, clockwise. Ooh. I'm not sure how gear 6 can be driven as drawn. Yeah, that's me saying that in the past right there. Clockwise. Oh, I know why. Okay. So no, I don't know why. I don't know why I got a negative sign right there. This should be, if this is a positive value right here, if I just say clockwise is positive, therefore this should be indication that it should be positive as well. Oh, I know. No, it's supposed to be positive. Yep, I got it. I just did math error, right? Because this is going to be a positive 3.182 minus NA, so it's going to be 2.182, and that's what I did. Yeah, okay, so I got the right answer. I got the right answer. Just bad at math. Okay, so I had a request from Nathan, I think. Can we do one that consists of free body diagrams and forces on a shaft? All right, so I have one of them as I was looking through here. I think this one constitutes that. It's a little on the easy side, but not too terribly bad. I mean, the same ideas kind of go through here. I'd say it's easy because the shaft is, obviously symmetric, although that happens a lot, it can happen. So not out of the realm of possibilities. And there's some forces here. They got 32 horsepower, 1800 RPM. Yeah, so let's do that one. 1334. 1334. Or do you have another suggestion, Nathan? Anybody can chime in, not just Nathan. We could pick something else out of the book, or we could pick a practice problem or anything you want to do.
Is this the 10th edition?
This is, yeah, what I'm looking at. This is the 10th edition, yes.
Okay.
I don't have an 11th edition as a PDF, so, and I didn't bring my book home with me. I'm looking at this problem right here. What they do a lot of times is they recycle, by the way, they recycle some problems. And so just in the problem, it says, redo. Well, I guess they didn't recycle the problems. I'll take that
Sir,
back.
can you do
Yes.
non-AGMA problem?
You want to do an AGMA problem? Okay, we'll do that. We were just doing the forces right now, but we could actually kind of invent our own AGMA problem if we wanted to out of one of these.
Okay.
We don't want to do. Are we okay with doing this problem? And I'm gonna go. No, I would rather do a more complicated problem. I want to do a problem from the book from your old exams.
Yes.
No one has an opinion. Okay, we'll do this problem. So
I'm looking through the past exams. Like, is there a better problem than this one?
I don't know. It's hard to say what better is, but yeah. I mean, some of the problems I wrote, some of the problems I just got from other books. I'm not for the old exams. I'm not saying I did a great job, and there are problems. Let me see if I can. I'll scroll down. I made this file too big. I'm looking at my problems. Oh, I actually did this one before. I actually used this one. Well, I guess we'll go with it. Why not? All right. So let me go back up. Sorry for the wasted time. Try not to waste any more. All right. Focus. There you go. Focus. So I'll draw the thing out. I like to draw. And then I'll draw. I guess these bearings are lined up. That's a nice one. The bearings line up. I tell you what, I'm having all kinds of flashbacks to teaching online. Really didn't enjoy it. All right, so what do we say? This is D, and this is C, and this is shaft B, and this is shaft A, and they're saying the torque is coming this way, and they're saying that's in, and this is shaft. I guess this is the label over there. B, and I guess this makes this A. And this is 3 inches and 3 inches. And this is gear 3, and this is gear 2. How come there's never a gear 1 is what I want to know. Someone needs to do some research. Please, someone do some research and tell me why. So this is 18 teeth. And this is 45 teeth. And the power, H, we use H in this book for power for some reason. I guess maybe for horsepower. I don't know. H, weird number. And an input of 1800 RPM. And that'll be A. Find the direction and magnitude of the forces of the bearings at A, B, C, and D. All right. So first, there's a bunch of different ways that we could start this. We might want to find the torque, or we could find the force, right? And in our book, we've kind of done it two separate ways, right? We did when it came to this force section, the force in here, we decided to use, or they decided, at least in US units, to use this, find a V and then find the WT from that. So I'm just going to show you quickly what that, the differences, or how to do it both ways. And you could do it either way that you'd want to try to get the forces set up right here. But first we need to know the pitch, right? They told us, it's got a pitch of 5 teeth per inch, right? So the pitch is 5 teeth per inch. Yeah, teeth per inch. I blanked for a second. So we need to know the diameters of the two gears. So we'll call D2 is going to be, remember, N2 over pitch, which is going to be 18 over 5. 18 over 5. So 3.6 inches. And I didn't leave myself a lot of room here. I'll just crush it in. 45 over 5. I should be able to do that in my head, but I'm going to calculate it anyway because I don't trust myself. And I was wrong. Terrible at math. Just terrible at math. Somehow I've been able to manage. But anyway, when you go to find the pitch line velocity, remember that you want to use the same diameter with the with the RPM, right? So this is the shaft, or this is the gear that's rotating at RPM. So you use that diameter. So we get 3.6 in 1800 RPM divided by 12, and that's going to get us a pitch line velocity, 3.6 times pi times 1800 divided by 12. Boom. 1,696, and these are feet per minute. And then we go back to our book because I don't trust my memory, and we could have WT, which is a subscript here and later gets turned into a superscript in the next chapter for some silly reason that I can't explain. I'm sure there's some reason for it. 33,000, and we have 32 divided by here, and maybe it'll fit right there. I don't know. We'll see. So 30, flip it around, 33,000, and I got 622.5 lb. It did fit. That's one way that we could approach this. Another way, like I almost kind of prefer this way, to tell you the truth. I like taking the torque instead, and that's under chapter 3, and under torsion. I mark this one in my book because I use it a lot right here, and you can see that we have this equation right here. So I like this guy right over here with the 63. So we could find that the H is equal to TN, torque times RPM, divided by 63,025. So we could find the torque by taking the power, which is 32 horsepower, 32, and multiplying it by 63,025, and then dividing it by 1800, right? Torque, and 32, 63,025 times 1800 divide. We get a torque of 1,120. These are inch pounds.
is not Tn equal to T?
Tn is equal to horsepower, right?
Yeah, shouldn't be horsepower time 63,000.
Yeah, 32 times 63,025, and then divided by RPM.
Why did we divide it by RPM?
I'm trying to find the torque. I hope that makes sense. Trying to find the torque. I'm just trying to show you, here's an alternate way to try to find this.
Okay, I got it.
Okay, so we found it this way, but using this equation, but instead we could use this equation, and I think by knowing both ways, you actually understand better, what is going on here instead of just plugging numbers in. So the torque will be very good. But if we were to take a look at our free body diagram, right? So we have a free body diagram here and a free body diagram there. And I've decided to look at it this way right here. I hope you don't mind. I just made that decision. Because on here, they're showing the torque going that way. Therefore, we're going to have a force right here, this force, and if we're going to label it correctly, it'd be F. This is 2 and this is 3, so this is 3 acting on 2 in the tangential direction. And I got to make enough room so they could be underneath that one. So I'm going to F 3 onto 2 in the radial direction.
Could you explain how we know F3 on 2 and tangential goes to the left in this point of view?
Okay, so this is going clockwise, right?
Yes.
This is T, and we can call this A acting on 2, that torque. So if we do the sum of the moments about and we didn't really give it I guess they did call this X, and they called this Y up above. So it's about some of the moments about the X axis, I guess, is equal to 0, and we'll consider counterclockwise as positive. We'd have negative TA2 plus, well, we need a plus, right? So this is going clockwise, so this has to go counterclockwise to be able to balance it out. Does that make sense? So we can say that F32T times D2, and I used capital D's for the diameter, didn't I? You could use lowercase d's, it doesn't matter. Equal to 0 right here. So we've just used this up here, negative 1,120 plus the unknown, this right here, times 3.6 over 2 equals 0. So we'll get F32T equal to, see, 3.6. I should be able to do it in my head, but I didn't. Divide, we should get 622.5 pounds. You see, you've got the same thing, right? We just used a different approach onto it. At one point, we probably want to get the torque anyway, so it'd be a good idea now to do it. Okay, so one thing I didn't put on here, I didn't label the bearings, or it wouldn't be the bearings, actually on the shaft, sorry. So we have, I like to use R's. I think R is okay. R, and this is going to be A acting on 2, and I'll call it in the Y direction, and R, A acting on 2 in the X direction. We're going to be complete come up to here as well. And this is going to be F2 acting on 3 in the tangential direction. Didn't leave a lot of room for myself in the F2 acting on 3 in the radial direction. And here we will see that we're going to have, I'll put these guys on here. So here's my reaction R. I don't know if I almost kind of wish I didn't put R, but that's all right. We're stuck with it. This is B acting on 3 in the Y direction, and this is R, B acting on 3 in the X direction. And now we want to look at our torque again, just like we did below. And this guy is making it go counterclockwise. So let me see if I've said the right way. This is making it go counterclockwise. So this one better make it go clockwise. Yes. Right. And we should say that this is the torque of B on 3. And we should find the sum of the moments. Once again, it's going to be about the, well, sort of about the B. It's kind of at the B. It's about this axis up here. It's about that axis right there. So I'll call it that. And so we're going to have, this is going to be F23T times D3 over 2 and minus my TB3 equals 0. And so this value is going to be the same, 622.5 times 9 over 2. So my TB3 is going to be equal to, let's see, I'll take it and go, 4.5, right? 4.5 times 4.5, boom. So we get 2,801 inch-pounds. Just if you wanted to double check right here, we want to know the RPM of this this gear, right? We didn't get that yet. So remember that you can do this a couple different ways, but I think the easiest maybe is to say NB is going to be equal to, well, you can go E times NA, right? And we could say that our E is a very simple one, driving over driven, which is going to be 18 over 45. I just did that wrong. There you go, 0.4. And so now we could just say NB is equal to 0.4 times 1800. So this goes 720 RPM is the output of shaft B. Notably, if you wanted to double check our torque up here, you could come back here and do the same thing that we just did a minute ago and check, right? And you would see that we would have like 32. I'll do it here. You go check torque. Check torque of shaft B. And TB is going to be 32 times 63,025 divided by 720 now. If I did it right, that is. I'm not guaranteeing nothing at this point. Oh, look, yeah, 2,801 inch-pounds. All right. So the mission of this problem is to find the direction and magnitude of the forces on these four bearings. I don't think we necessarily need to do all four bearings, but not too
Sir,
terribly. Yes.
are you gonna upload the notes like you wrote later on?
If you want to, if you want
Yeah,
me to.
I didn't write everything because I tried to follow you more
I
to
got you.
understand it.
I got you. I'm sorry if I'm going too fast.
No, it's okay, sir. Thank you.
You're welcome. Anything for you. Let's see. Okay, so what we need to do, we have a sort of a setup right here. We want to try to draw an FBD in three. Actually, I could actually even tell you that there's actually a sort of a trick that we can kind of do in this one. There's a shortcut, but we won't necessarily do the shortcut. But we could do the shortcut because this thing is on a. There's on an one thing we haven't done yet. I'm sorry. We didn't get the radial forces, right? We got the tangential forces, but didn't get the radial forces. But we could do that on here, right? So the radial forces, I forgot. They're going to be equal to each other, right? The 3-2 radial equals the 2-3 radial, and there's just going to be the force 622.5 times the tangent of 20, because that's the pressure angle. And goes 622.5. And so we get 226.6 pounds. So either shaft, actually, we'll pretend there's a coupling over here that doesn't that's going to make it so the load doesn't the up and down and side to side load doesn't get transferred over onto this thing, but torque does. I guess this is the output one that I just drew because I just drew it over that side over there. I like to make them side by side. And here's
Is it just where we do a shear moment diagram?
Well, we could do a shear moment diagram, but we weren't asked to do the shaft design or get the shaft, so we don't necessarily. But it is like, yeah, this is where we would start doing. If we had to do the shaft, that's where we would do it. But we go ahead and this one is going to be the Y direction, and this is going to be the Z direction. All right, we're going to set it up to, because let's see over here. We want to get these reactions, but it's a really simple one because they're symmetric, right? It's 3 inches and 3 inches. So, you're just going to take half of the force and place it on each side. You can almost cheat and just jump and skip the whole thing, but we'll pretend it's difficult. Let me, 1 second. Okay. So the only challenge here is to just make sure that we're putting the forces on here. So I started with this one. So in the Y direction, it's going to be this F23 radial, and in the Z direction, and we're looking down onto the thing, and if you're looking down on it, on the down direction, Z is pointing to the left, so this is going to the right. So this is going to be like right here. It's going to actually be underneath this gear, and that'll be the F23 tangential right there. But we're just going to have reactions right here, and that's why I kind of said I kind of wish I didn't use R's in here, because this is actually the force that the shaft is feeling, but that's okay. We go R, this is D, and y, and this is r, c, and y, and then this would be r, d, z, and r, c, z. And then these dimensions are both 3 inches on either side. So some of the moments, it's kind of ridiculous to do this, but that's right. There you go. All right, well, that's going to be, do about D. So we're going to have a negative RC times 6 plus, because that's going clockwise and that's going counterclockwise, plus this radial force, which is the 226.6. So RCY is going to be it's supposed to be times 3. Sorry, forgot my moment arm. It's 3, right? Because we're going to do it around here, so it's that times the distance. So so we're really just dividing it by 2. Duh. 113.3 pounds. And then if you were to do this as we typically would do, we'll find the other, and we'll go negative RDY plus 226.6, and then minus 113.3 equals 0, and the sum of the forces right there. And then RDY is 113.3. Kind of silly. I mean, same thing true here, where this is 622.5 right there, right? So by inspection, don't be like me, kids. This is bad. Don't do this. You could say that RDZ equals RCZ, which is just going to be 622.5 divided by 2, 311.3, call it, pounds. So you could see that the reaction at D and the reaction at C are both going to be equal to the square root of 113.3 squared plus 311.3 squared, or 331.2 pounds. And truth be told, that's going to be the same thing for the other set of bearings. They're just going to be pointing in a different direction. So like if you wanted to take a look at what that looks like first, you know, you're going to take a look at that bearing right there, the reaction that's happening right here. In the y direction, it's going downwards. And in the z direction, it's going this way. So that's going to be a force that looks like that, right? And that's going to be the bearings acting on the shaft. So if you were going to go the other direction, the load that's actually on the bearings is actually going to be in that direction right there. And it would be, let's see, the Z is this is the larger of the two, so it would be the rise over run should be 113.3 divided by 33, 11.3 divided inverse tangent. So you have almost pretty close to being 20 degrees. Does anybody recognize why that is? Should be 20 degrees, right? That's the pressure angle on these two gears right here, right? We have these two gears, and here's the line of action right here. And the actual load, the actual force that's being applied there is this right here, right? This is the total force, the W. Of course, and I'm violating my own rules by showing a force arrow without doing a free body diagram here. But here's the total force, right? That's broken down into parts right there, right? There's the transmitted, and then, or you could say the FT, and here's the FR. If here, I got to get rid of it right there, right? Boom. So one way that we could have simplified this, because there's only one gear on this shaft, is we could have just rotated the plane to be in line with this right here and done a single. So here's that same shaft that we're doing right here. So I don't know if this is really good for exam prep, because this is just information you'd want to know, right? That we could just have, if we're drawing, so we're looking down perpendicular to the plane in which the total force happens onto the thing, we'd have this W right here, which is of course going to be, could do it a couple different ways. Maybe the easiest, well, I'll just go ahead and take that, the square root of that, and that together. Excuse me, square root of the radial and the tangential together is the total load onto the thing. You could also just divide that by the tangent of 20 degrees. And so 622.5 squared 226.6 squared atom square root them, and you get 662.4 pounds. And of course, you're going to have, here's the bearing reactions at D and C, and they're just going to be 1/2 that. So they equal to 331, right? Which is what we had right here. So when I said that this was sort of an easier, when I'm looking at this going, this is actually a pretty easy problem. It's because of the symmetry. It's also because there's only one gear on each.
In our case, sir, do we need to do the last few steps you did?
Oh, no, not at all. No.
Okay.
I'm probably, it's probably a mistake for me to try to teach during the exam review session. So I was trying to show you a bigger picture of what was going on.
Okay, thank you, sir.
Let's try to do stuff that actually will help you prepare. All right. So you asked for an AGMA problem?
Yes, sir.
Okay, so you have to concede that AGMA problems can be pretty long. So we're not gonna on a thing here. One second, I'm just trying to see what kind of problem. It's going to be somewhere in the, sure. Let's do this one. Problem 1422. So let me, I'm just going to keep track of my pages right here. So this is 1334 continued. When I go to scan it as requested by us. Okay, so a spur gear has 17 teeth. So go N2 equals 17. and I don't know, I guess I'll like P for pinion. The pinion has 17 teeth, and the gear has 51 teeth, and the pressure angle is 20 degrees like it always is, and the overload factor is 1, and the pitch is 6 teeth per inch, and the face width F is 2 inches, and the pinion RPM is 1,120 RPM, and the life cycle is 100 million revolutions. Like, so, I'm trying to think of what we do. I'm gonna go capital L. Sorry for joining in a late hour. Just got out of lacrosse practice. No problem. I'm afraid of lacrosse, man. The balls go too fast. 10. So that's 10 to the 8 revs. Reliability R is going to be 99% reliability. Quality is 5. And material is a through hardened. I'm writing all this down. Sorry. Hope that's not a waste of your time. Through hardened steel grade 1. And with a Brinell hardness number, BHN equals 232 core and case for both gears. We want a safety factor of 2 and rate the gear set for these conditions using AGMA method. So I'm only going to do the bending one. And by the way, these are like in between numbers that I've provided as part of this. So we would have actually, we will go through and use the book and go through the process here. So we go through and onto the book, into the section. And of course, you were going to go, see, I think if I could dual screen, or I can just set it up to the side. Can I do that? Let me see. Set up to the side? Sure. I can't really quite see that very well. We'll zoom in. Oh, darn. Sorry. Down here somewhere. Where you go? Should be like somewhere in here. Oh, analysis. There you go. Move you this around. All right, so we'll write down our main equation here. Sigma equals WT KO KV KS PD over F, and then K looks like that's KM, KB, and then J, right? And there's a little bit of like which one should we do first? I should also I'm going to write down this guy right here, my allowable, because we're going to set these equal to each other. So we go allow is going to be equal to ST over YN divided by KT and KR. I'm also I've decided that I'm only gonna do we're only gonna do this for this example because we want to do other examples. Because like I said, these are really long. It's a long problem if you want to do. But it's also, you would have to do this for the pinion and the gear. So let's just do the pinion only. Are we okay with that?
Yeah. Do we also have to divide by a factor of safety for sigma
Yeah,
allowable?
you're right. I lost my train of thought at some point. So I'm going to SF. Yeah. So let's start out with the ST. Let's look him up. Good place to start. And whoop, did I go too far? No. Somehow I started going backwards for some reason. And we have to pick the right one from here. That's the contact one. Of course, you're not going to do this during an exam, but if you were to need to do this, generally, I would say the procedure is to consult this table so that you're able to figure out which graph that you would want to use. I can't remember what we said. It was a through hardened steel grade 1. I think so they had through hardened, they say to use, and here's grade 1, say 14, so use figure 14.2. I don't think they say anything about the flame induction or carburized or nitrided. So we're really just going to look at 14.2.
So on the exam, which values will you be expecting us to be looking through or be trying to find for this
I don't know
equation?
yet.
Okay.
I don't know yet. I haven't written the exam. So I mean, you could take a look at older exams, although you should recognize that in some of those older exams, I think I make a mark by it. Some were for like just the order in which it is. Sometimes the second exam in many classes I do like this, I make it a take-home exam, and so some of them are longer problems than you could do during an exam. And so like I used to do that, but I've moved the gear stuff to the beginning of this semester because of the way that I wanted to have our project organized. So we're not doing a take-home exam for the gear stuff. So just recognize I can't ask. There's just a practical limit to how much you can ask and expect students to be able to finish. And I've missed that mark a couple times. So we're gonna do our best, and I'm gonna reduce as much as I can. And I'm still gonna have students who don't finish because I don't know, just can't seem to find a way to keep everybody happy. But you're just gonna have to go as fast as you possibly can. No, that's not true. But anyway, we want grade 1. And so I'm gonna write that equation down. Unfortunately, I'm not keeping my thing as organized as I would like to. I'll try to squeeze them in here. But that's the ST. We're gonna have 77.3 times HB plus 12,800, right? So we were told that our Brinell hardness number was 232. 232 plus 12,800. So
Can you just convert those values in front of
77.3.
the hardness number to PSI? Because in the 11th edition, they have it in megapascals for some reason.
Really?
Yeah.
You sure?
Mm-hmm. Same figure number, same graph, just with
That
the
sucks.
curves in megapascals.
Well, I guess I won't ask that then on the exam. So 19,214 psi, or 19 k, 19.2 ksi. Okay, so we're gonna go for yn. Fortunately, it's this is I'm not taking the most efficient route here because this is, I believe, yn is like near the end of this. We're jumping back and forth. Yn right here, and I'm just going to go for the pinion. You have to kind of look through here and decide which curve to use we were told 10 to the 8, right? So we don't have to do, if it was for the gear, on this, we would use a different YN because it's rotating less RPMs. But we'll use the 10 to the 8. And we have to use sort of a judgment call in this area. I'm going to go ahead and use the top equation because I want to. I could use the bottom equation. It says the choice is influenced by this stuff right here. But as we've said, noted before, hopefully, these are engineering judgment things, maybe based on experience, but also noting that getting too tied up into, well, what happens if I pick this one instead of that one isn't really like helpful, because we could like the things like the overload factor, if we weren't told that, we could have vastly changed what the results are just by making an engineering decision on that. So these little nuances maybe kind of put it in perspective. Negative 0.0323. And so if we shove in our number of 10 to the 8, that's not 108, but we get 1E8.0323, make it negative, raise it to it, 1.6831, multiply it, and we get an exciting 0.9283. The other two things, the KT and the KR. Let's see, the KR is reliability factor. We can just look it up. So you see 0.99, therefore equals 1. The temperature, we can just assume it's equal to 1. Right here. Let's say that it's 250 degrees. That's good by me. Cool. So we have the allowable is going to be our 19,214 times 0.9283 to 2 divided by 1 and oops, I forgot a safety factor of 2, right? So it's all in my calculator still. Okay, cool. Multiply it and 2 divide. So we get 8,918 psi. Ooh, wow. That is out of focus. Focus. Why aren't you focusing? What's wrong with it? Technology hates me lately. Not everything's about you. There, oh, there you go. Okay, we're coming back. Can we? Ooh. All right, so we come back over onto this other side here. So we're going to set that equal right there when we get to it. Okay, so KO, we were already told that was equal to 1. We need KV. On an exam, do not try to use the equations. If you use the equations and you run out of time, it's your own fault. What you do is get the pitch line velocity. So, one good thing to start with, by the way, a lot of times we would want to know, need to know, should we? Well, I guess get the diameter first, get the pinion diameter. So that's going to be 17 divided by 6. 2.833 inches. So our pitch line velocity, which might actually, I think they actually have on the funny blue page right here. Yeah, they do. They give you the equation for the pitch line velocity. Kind of nice of them. So pi 2.833, and we said it's 1,120 RPM. put it underneath there. So 1120 times pi times 12 divided, and we have 830.8, which is kind of slow, feet per minute. So we can kind of expect a low kV. The dog has joined us. The dog is here. We should take a dog break. All right, so this is kind of a tough one to read, but I don't want you on an exam to use the equations. Don't use the equations. You're going to be wasting time. Just do your best. There's 1,000 right there. Move over a little bit. There's 800, and we were told it was a Q of 5. So, what do you think? 1.55? We're going to take a vote. It looks to me like this is about halfway right there, right? That's about 1,000. So kind of like right down in there. I think 1.55. And to cover my tail, when my boss says, "Did you calculate this?" No, I just looked it up. I put the little squiggles in there, squiggle eagles. So we got that. So we got that going for us, which is nice. The Caddyshack. Size factor. How many of you are going to start trying to go through this equation right here? How many of you will? But then always say, you may set this right here. That's all you needed to read. Just read one line down. Even below it says use KS equals 1. I don't know what they're talking. If KS is less than 1, use KS equals 1. There's a whole lot of reasons to use KS equals 1. Let's use 1. So we have, so far, everything covered. We know this. We need KM and KB and J. That's all we have left to do. So we go find KM, and we recall what a tedious process this would be to get all of these C's and these C's. So you can be assured that Dr. Deal will either give you KM or tell you KM is equal to 1. Because I'm not going to make you go through this process. For one thing, we don't know a lot of these things, right? It's all about where the gear is on the shaft, right? So let's just not even worry about it. The load distribution factor, 1. And then we got the rim factor is KB. I think that's my recollection. Let's see if that's true. Hardness ratio doesn't apply. It must be up higher. Yeah, why would they make that easy on us? Put in that place. Why would they? We can make it dizzy. Where you at? No, I think I lost it. I don't know where it is.
It's where figure 1416 is.
It's where 1416. Oh, so it's way back there. Okay, so let's just noteworthy that it's the rim factor, and we're going to set it equal to 1. It too is going to be 1. So all we have left is J, and we remember that we have 17 teeth and 51, but we're doing this for the pinion, so I'm going to write down what the J is right here. We're going to do 17 teeth, and darn, 51 doesn't even intersect. So what we're going to do is we're just going to use where this intersects right here. I bet if we were to read down in the instructions for this chart, like below 17 teeth or something along those lines, it would say just pick where it runs into the line or something along those lines, I think. I don't know. But that's what we're going to do. So it looks to me, guesstimating, that's going to be 0.295. You can call it 0.29. I'll accept 0.29. Doesn't matter to me. So we had everything we need. I think we can put this aside. Go back to the full page and write this out where we have 8,918 equals WT times 1 times 1.55. 1. The pitch was 6. The face width is 2. The KM is 1. KB is 1. And the J is 0.295. So we have ourselves 8,918 divided by 1.55 multiplied by 2 divided by 6 and multiplied by 295. Boom. So we have 565.8 pounds. And so if we want the power out of that, we can find H is 33,000. I think it's even on the wonderful little blue page. I go too far. There you go. Oh. Do I have to divide? I have to divide. Yeah, that makes sense. So we're going to go WT times V divided by 33,000. 565.8 times 830.8, 33,000. Just want to point out to you, the magic of the Hewlett-Packard calculator is that when you do engineering calculations, the numbers just kind of work out. So I just have to go times and 33,000, boom, and I can go, that's 14.24 horsepower. That's why I can. So I think it's the TI-89. That's why students take so long. That's my new theory. Why students can't finish exams is because the TI-89 has too many buttons to hit. This reduces your buttons by about 25% of the number of buttons that you have to hit. Trust me, you go fast. And you get all kinds of street cred as an engineer for an HP. There you go, HP 35S. Just saying. I had a professor that convinced me HP is where to go. Her name is Aline Chubb. She convinced me. All right, so let's we did an AGMA. Let's do a bearing thing. We haven't done any bearing things. What do you say? Yay? Nay?
Sounds good to me.
All right, cool. Some of these I hate. There's a couple of these problems that I'm having flashbacks, I recall, but I didn't like them. I really need to get rid of the answer right there, because we should see what the answer is. The ones I didn't like. I'm trying to think about the ones I didn't like. There were conceptual problems that boggle your mind. I'm trying to remember. Just want to stay away from them. That's what I'm gonna do. All right. It's in chapter 11. Right? Some of these are just plugging and chugging. Doesn't make for a great question. All right, let's try this one. No, that's got an axial. We don't want to do the axial one. That takes too long. Just pick one of these. I don't care. Pick one. All right, so let's pick problem 1112. Nah, 1113. Go 1113. Problem 1113. Where we have 11 kips. I don't like kips. 11,000 pounds is what they mean. So here's my FD, we'll call it. And we got a Laverne of 20,000 hours. And again, RPM of 200 RPM. And our desired reliability is 99%. So for the bearing load application specification in the table for the assigned problem, determine the basic load rating for a ball bearing with which to enter a bearing catalog of manufacturer 2 in table 11.6. Assume an application factor of 1. So this is a pretty straightforward problem, right? Go to our bearing section here. Nope, not to you. Still bearings. And we got a reliability thing here. So our best bet is to go with this equation right here. This is the one I like. I'll write that one down. C10 is equal to AF FD times XD divided by XO plus theta minus XO times the natural log of 1 over the desired reliability, close bracket, raised to the 1 over B, and to the 1 over A. And now I need to get these little factor things.
What's the difference between the ln one and the one where you're not using ln? Where's 1 minus RD or just the ln version?
This is for people who don't have a natural log on their calculator because it was back in 1980 or so. I don't know. Or nobody's calculator had a natural log on it. And people who were getting the Radio Shack calculators with solar powered. If you're lucky, you had a square root on it. Because times are changing. So I have a copy of a book that predates Shigley. It was from 1943. And it's obviously where Shigley got a lot of his stuff from. And it even has like a syllabus enclosed. I got it from Abe's book. I bought it for $1. But I was just curious to see what it was. And so some things haven't changed. It didn't bother to change it. In the next edition, probably won't bother to change it. There's a couple things wrong, and I check for them when the new editions come out. Sure enough, they stay wrong. All right, so and as I mentioned, if I ask a question, I probably will give you some chart of what this thing looks like right there. And I have actually to answer your question, besides with the sarcasm, Dylan, you could graph this, right? None of these things change. It's just with the reliability. So if you have like an RD, and I like to call it an RF, like reliability factor, to give it a name or something like that. And I can't remember which way it goes. It goes up or down. Actually, I could probably find it in old exams. So let's see what here. Let's see from. Oh, I haven't done an exam. I didn't look at the old exams. Let's go. Fall 19. I don't know which exam it's going to be. Exam 1. And on the video, you could stop this. You could stop. You could pause right on top of this as I fly by these questions, and you can find new questions right here. Does this one have? Boom, 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 boom. There you go. That's generally what I'll do right there, right? So if you had 95% reliability, you find that it's 0.6 is the reliability factor, right? Instead of having to go through this pain in the tuchus right here. But let's do that as we're coming through here. So we got an application factor of 1. We have 11,000. So we need to look that up. Good to know where stuff is in the book. So come back into the appendices. I wish they had the little bookmarks in the appendices. Useful tables. Thanks. But they have a conversion factor thing right in here if you needed it. And we want to go, let's see, multiply pounds to get a newton. So we need 4.48, 4.45. It's actually 4.448 is what people usually use right here. So, and then we have to divide by 1,000, right? So we go 11,000 times 4. We'll go 4.5 because that's what they said, and then divide by 1,000. And that's going to get us in kilonewtons. So happy day. We also need an XD. I guess I could do that over to the side. If I would have been more organized, I would have recognized that I needed to do that. Says we need an LD, which is going to be, let's look up the equation. I know. We don't have to look up the equation, but let's look up the equation anyway. Because I think Osama would ask me where I got the equation from if I just wrote the equation. I don't know. Is that presuming too much? Right there. Boom. There's the equation we're going to look at, right? We could also just like rationalize it out. That's like, okay, we have this many hours and we know the RPM, so we can turn it into, instead of revolutions per minute, revolutions per hour or something like that. Yeah, 60 minutes per hour. So 60 times L times N. So it's 60 times 20,000 times 200. Turn it on. Begin. So we get 2.4 e to the 8 revs. So our XD is going to be our LD over the manufacturer. There's manufacturer 2, so that's just going to be 2.4 E8 over 1 E6. Do that in our heads. But I did on my calculator anyway. 240 is our ratio. So put it in here, 240. And then start with this business, monkey business. What kind of business is this? This is monkey business. 4.459 minus 0.02 natural log. Sounds good, like a good thing, right? It's a natural. That's just natural. Oh, did I actually? I looked at the wrong thing. I know I looked at 95. I think we need to look at 99. See, we got to see what our goal is again. 99. Ooh, wow. That's like 0.2 something. We're about to find out. And then raised to the 1 over 1.483. And then A for ball bearing is 3. Boom. Okay, so let me, I just want to calculate what I am calling the reliability factor right there. I'm going to do that first just to check the thing out and see if it makes any sense. So I'm going to start backwards over here, and I'll take 0.99 and take the inverse, and then take the natural log, and then I'm going to raise it to the 1.483, but inverse and raise it to there. And now I have to multiply it, and we could actually kind of do this in our head, right? We could go 4.439 times, and then add 0.02 to it. Boom. And this, by the way, becomes 0.2196, right? Or if I gave you this graph, you could go, okay, 0.22, 0.22, is that okay? 0.22 versus 0.2196. I think 0.22 is fine, personally. And now I can divide that, 240 by that, and then raise it to the 1/3. Boom. And by the way, all of this thing becomes 10.3. So it's like a multiplier by that. So 10.3 times our 11,000 times 4.45 and divided by 1,000. And we get a lot. That's a big one. C10 is equal to 504.2. I'm not certain I didn't make a mistake somewhere along the way. That seems like a pretty big number. So I don't think we'd be able to find that in our catalog. Not in our fake catalog here. Is the fake catalog here? Yeah, that's way too large. We can't find that. What about here? Oh, we might be able to. Yeah, look, we could if we would need to use like an O2 series, 03 series roller bearing, right? Somewhere like right in there. Because that's a large number. But anyway, that's the way we would proceed. So pluggy and chuggy. We got requests. We got another 8 minutes or so.
I had a question about this process.
Okay.
So when we find our C10, I was watching one of the lectures for that. That was the one class I missed, and I saw that we repeated the process to get the smallest bore size that we could. How do we know how many iterations to do, and when do we know if it's like a good bore size or not?
All right. So the one that you're referring to is when we have an axial component. I'm pretty sure. Because we don't need to do iterations unless we have to find a to combine the axial with the radial to get an equivalent thing here. I would say the number of iterations is really just dependent that you have a pretty good amount of confidence that if you did another iteration, you wouldn't get any different result. It's not something I would ask on an exam because it just takes too much time. But going back to what the concept is quite simply, it's an apples to apples thing, like another instance of an apples to apples, and that the manufacturer is giving you a rated load that's only based on radial loads only. So they're giving you a method to convert your axial load and radial load into an equivalent radial load only thing. And by way of empirical, values over enough bearings being broken in their little bearing testing unit, they found that there's a correlation down here. It unfortunately has is tied to the ratio of the axial load to the bearing's static load rating, that's CO, that's also in there. So in order to find this, you know the process where you have to pick a bearing maybe to start with, or another way to do it is just to ignore the axial load and then find what rating you have, go to the catalog and use that bearing, or maybe even just use the next bearing up might make more sense. And then go through and size, check, you go through this process right here, which is mostly consists of finding what this Y is going to be that you're going to put up into here, so you can find this equivalent load. Shove that equivalent load into the thing that we just did, except you'd put it in right there. And then see if if your rating is greater than or less than the bearing that you just used. If it is less than the bearing you just used, that's your answer, right? That's when you don't have to do any more iterations.
But if
But
it's more, then that means that use the one that you used previously, that you can't do any iterations to get a better size.
I'm trying to, let me see if the way that you said it made a little, could be misinterpreted. I'm trying to, if which is more. If the C10 that you get is less than the C10 of the bearing that you used to get this value right here, right? If it's less than less than the C10 that you associate with the static load rating, the CO of that, then yes. If it's less than that, then you don't need to proceed any further. But if it's more, then you have to do another iteration. You could probably get away with maybe taking a shot in the dark and picking a larger bearing after your first iteration, so that you don't have to have a third iteration, right? So if you're going in your second iteration and you're like, it's really close, the next bearing up, like pick the next bearing up, right? And then good chance you're gonna save yourself an iteration. But I'm not asking that question on that.
Gotcha. Thank you.
You're welcome. All right, so I'm a little burned out here. I'm gonna call it. I know we got 2 minutes left. I hope this was helpful. There are videos from, I think, 2 other sessions. I think spring 2020, spring 2021. I don't know what happened to spring 2022. I'm pretty sure I did one. Oh, that might have been nobody showed up. I think maybe nobody showed up. I actually had a no-shows, but I did it in person on a Friday, so it's my own fault maybe. I guess nobody could just make it, so I was like, all right, cool. All right, thank you. Everybody have a great weekend.
You as well. Thank you so much.
You're welcome. I'll stop recording now.
Thank you very much, sir.
Thank you.